spin the air inside of the box for us. And down here at the bottom we have water atomizers. Water atomizers take water and they turn it into a mist or fog-like effect. They're typically used in things like ponds or water features. All of this together is going to work to give us an example of a tornado in captivity. So, as soon as we flip that switch on, our fan will kick up, and this will begin to create some movement inside of the box itself. And now we see our tornado. Now, you may have also noticed that we have these gaps cut into the box. This is to allow airflow from outside to inside, because what we're using to create our tornado here is Bernoulli's principle. We're using a difference in air pressure. Bernoulli's principle states that a faster moving fluid has less pressure. The fluid in question here is not only the water molecules from the atomizers, making it visible, but more specifically, the air. The air around us is considered a fluid. So as the fan up top starts to spin the air inside, the air in the center of that vortex is moving faster than the air outside of it. So that is our faster moving fluid with less pressure. So the center is our low pressure system. Outside of that is our high pressure system pushing in towards the center. All of this works together and gives us this repeated sort of process, creating our version of a tornado. Now you may have also noticed, it's not that strong. It's a very weak tornado. Tornadoes in captivity, not that strong. However, tornadoes out in the wild, incredibly strong. Tornadoes out in the wild can spin up to 300 miles per hour. The top of the funnel can be up to 5 miles wide. The bottom of the funnel can be up to 2 miles wide. In fact, the widest tornado recorded touching down was 2 miles wide here in Oklahoma. Now, in order to get a tornado out in the wild, you need to start with something called a supercell storm. Supercell storms are a bit different than your average thunderstorm because they have something in them that tornadoes need. They have a spinning vortex of air already in the middle. As it spins, it starts to kick warm air up, cool air down. If that happens enough, it will actually begin to tilt. This will speed up the process, causing that funnel to spin faster and faster, and that can actually cause it to elongate. Once it elongates and touches down to the ground, that is when we consider it to be a tornado. So, of course, this is the part of the show where I have to say, if you hear those tornado sirens kick on, please, please, please get to either a tornado shelter or a central room in your house with no windows, something like a bathroom or a large closet. Please do not stand on your front porch and record it while sipping sweet tea. Oklahomans, I've met you. Y'all did that last week, didn't you? Got weirdly quiet. I'm sensing shenanigans. All right. One more round of applause for Wendy, everybody. Liquid nitrogen is negative 320.4 degrees Fahrenheit. It is incredibly cold. It is nitrogen gas that has been cooled, compressed, and condensed down to that temperature until it becomes a liquid. Now, when that happens, we have to keep it in special containers like this. This is called a dewar. This dewar can hold up to about 30 pounds of liquid nitrogen at a time. Just a fun fact for you. And this is what liquid nitrogen looks like. It can be a little difficult to see. But more importantly, do we all see the cloud that's already coming off of this? That cloud right there? That cloud shows us liquid nitrogen expanding back into gaseous nitrogen like that. It happens instantaneously because liquid nitrogen's boiling point is the same as its liquefying point. That means anytime liquid nitrogen comes into contact with something room temperature to us, that's over 400 degrees warmer than liquid nitrogen. It's going to flash boil. Now that flash boiling can actually look pretty cool. It can create something called the Leidenfrost effect, the Leidenfrost effect, which looks like this. If you've ever had a hot pan on the stove and you pour water on that pan, you may have noticed the water beat up and skid around. It's the same effect that's happening. What's going on is the liquid is boiling so quickly that it's not actually touching the ground. Instead, it's rolling on a pocket of its own expanding gas, keeping it hovering just above the surface of the stage here. So we're going to use that incredibly low boiling point and expansion rate to help produce our cloud. So of course, as I mentioned, we already have a cloud that comes off of this, but as you may have noticed, it's pretty wispy. It's not very full, it disappears really quickly. Now I can't get a cloud to hang out for too long, but I can get it to be a lot more visible, for sure. There we go. You need a pretty specific amount of liquid nitrogen for this. But you don't need just liquid nitrogen. In order to make this more voluminous, more visible to everybody, we need to add moisture. And the best way to do that is to literally use water. So back here behind the desk, I currently have an electric tea kettle bringing water up to its boiling point. Does anybody know the boiling point of water in Fahrenheit? You can just shout it out. Yeah, 212 degrees Fahrenheit, absolutely correct. If we're talking Celsius, it would be a lot easier to use 100 degrees Celsius, but we're in America, we use Fahrenheit here. So, we're gonna get an equal amount of water to our liquid nitrogen, just a little bit more. Fun fact, clear liquids are hard to measure in white cups. You can't see them, they disappear. All right, now I'm gonna mix these two liquids together into this empty cup right here, and we're just gonna see what happens. Bless you. All right, now from the audience, I do need a little bit of help. I need you guys to give me a countdown starting from 3. Go ahead.
3, 2, 1.
Here. That was helped along by the added moisture from the hot water. That hot water warmed the liquid nitrogen up incredibly quickly. It's like a 530 degree temperature difference between those two liquids. And the liquid nitrogen actually helped cool down the water, causing it to condense, giving us more of that water vapor that we saw. Now what we're left with is water on the table, and water on the floor, and a little bit of water on me, but I mostly dodged it whenever I stepped back, which is always good. And as for what's left in my cup, it's nothing. There's nothing left. All of the water actually got sort of thrown out of the cup by the liquid nitrogen expanding so quickly. So anything that I aimed for in here just got shot right back out, and thus is now on the floor, which I'm gonna have to clean up later, but that is, again, a me problem. So, this is very similar to clouds out in the wild, because in order for a cloud to exist, you need hot, moist air and cool, dry air coming together to create that visual effect that clouds are. Now, clouds up in the sky also live in very specific conditions. They need a specific kind of pressure system. They need to be in like a very specific location where the temperature is just right, which of course we can't really replicate in here because that would be like just above freezing, and I don't want to live like that. So we're gonna keep it a nice like 70 in here, and I'll just make clouds that last for 2 seconds. You're welcome. All right, so now that we've talked tornadoes, clouds, thunder, and lightning, it is time to blow something up. Now, of course, it's not what I meant to do, but I have it anyway. Of course, we are going to be using liquid nitrogen to achieve our explosion today, and of course, some of the things that we learned through weather. So we're going to use that increase in pressure and temperature that we learned about to achieve our final explosion. For this to happen, we're going to use a 2-liter soda bottle. Now, 2-liter soda bottles are typically rated for about 160 psi, or pounds per square inch. What that means is they can usually withstand up to about 160 pounds per square inch of pressure before they rupture. I'm going to fill this bottle up about 1/4 to 1/3 of the way full with liquid nitrogen that expands up to 700 times its own size in an instant. So, when I cap the lid onto this bottle, that liquid nitrogen inside is going to continue to expand and expand and expand until what's going to happen to the bottle? It's going to explode. Everybody's favorite time of day. Now, for this particular explosion, I cannot give you a countdown. I can only tell you when to cover your ears. Because this is a pressurized explosion, it is going to go off when it wants to go off. So if you do not like suspenseful explosions, this is probably not the one for you. Take a moment right now and exit the theater if you feel the need to do so. While you're making that decision, I'm going to get my safety on.
Pretty loud.
Are we ready? Fantastic. Go ahead and cover your ears, cover your
still hear the phone. It would have been cool if the music ended one. Explosion, let's see.
Oh my gosh, the whole lid is on there. There we go. That's fun. That's cool.
The entire lid went flying.
So, someone might fact check me on this, but I did hear at one point that the cap of this lid, whenever this launches, moves like at the same rate as a ship launching, like a rocket ship launching. I don't know what exactly to Google to learn if that's true or not, but somebody told me that once and was like, that sounds cool. So now I've given you this potential information. If you know what words to search for Google, please let me know what you find out, because I have yet to actually find anything. But nonetheless, that is the entire cap of this bottle right here. You can also see that it's got some pretty sharp edges on it. Not the best, but don't worry, we'll take care of that. Now, we're also left with some pretty good chunks in here. There we go. So these are chunks of the same tuna bottle that I just threw in there. You can see that they are covered in ice. That's because we keep about 2 to 4 inches of water in the bottom of this container. That water helps speed up the process of the liquid nitrogen expanding, leaving us with this right here. Now the second explosion is called a BLEVE. BLEVE stands for Boiling Liquid Expanding Vapor Explosion. Very violent, as we can tell. Also incredibly unpredictable. There's no telling exactly when a pressurized explosion like this is going to go off, which means we should not try this at home, correct?
Yes.
Correct. Because that's illegal to do without a permit in Oklahoma.
The more you know. The more you know. I know that.
Y'all keep admitting crimes to me. You should stop.
The more you know.
What about Texas? As long as you are not within city lines. I am from Texas. I checked.
The more you
Sorry,
know.
you had to find out that way. Anyway, that is all that's left of my tuna bottle. That is all that's left of your weather show.